Imagine looking at a massive, tangled knot, pulling one single string and watching the whole thing fall open into a perfectly straight line. That is how we want to handle a math problem like this. Solving this by hand used to mean hours of tedious, error-prone scratching on paper. Let's just cross that out. We don't need to do it that way. Instead of fighting through the arithmetic, we can translate these numbers into an entirely different language, a mathematical system where these difficult operations simply don't exist. By moving the problem into this alternative format, we bypass the brute force calculations entirely. The hard work just disappears. To perform this translation, we use a logarithm table. It looks like a dense wall of data, but you can think of it as a translation dictionary. You look up a standard number, and it gives you its log equivalent. In this new language, numbers follow simpler rules. Multiplication morphs into basic addition. Division snots down into simple subtraction. Finding a power becomes a quick multiplication, and finding a square root is as easy as simple division. The table is a tool designed to take high-level, complex math and downgrade it into the kind of arithmetic you learned in elementary school. Let's translate a number, like 46.75. To convert this, we split it into two pieces, one that tracks its overall scale and one that tracks its specific sequence of digits. We handle the scale first. In the log world, this is known as the characteristic. To find it, just count the digits to the left of the decimal. Here we have 2, and subtract 1. That leaves us with a scale tag of 1. For tiny numbers, like 0.046, we do the opposite, counting the leading zeros to find a negative scale tag. We set this scale tag for a second. It stays separate from the rest of the translation, acting like a bookkeeping label for the size of our number. This ensures we never lose track of how big or small our number is, whether we're dealing with millions or microscopic fractions. Now we look at the specific pattern of the digits, the part mathematicians call the mantissa. To find it, we ignore the decimal point entirely and just look at the raw sequence, 4, 6, 7, 5. We find this pattern using map coordinates. We scan down the left column for the first 3 digits and across the top row for the final digit. Where they meet, the table reveals our translated pattern, 0.66978. Finally, we take our scale tag from before, the 1, and attach it to the front of this decimal. By merging the scale tag with our grid lookup, we successfully translated a real-world number into its perfect logarithm equivalent. Sometimes a number is too precise for the book. What if you have 4.6793, but the table only lists 4.679? We look at the gap between known entries. The total distance between our logs is exactly 9 units. Moving 30% across that gap gives us 2, which we add to our starting log as a tiny correction. This method of estimating the values hidden between the printed numbers is what engineers call interpolation. This technique allows us to handle incredibly precise measurements without needing a book that is thousands of pages long. Now that our numbers are translated, we apply our simple rules. That terrifying multiplication problem from the beginning is now nothing more than basic addition. Once we add those logs together, we get a new number. But the table is a two-way door. To get our real-world answer, we have to translate that log back into standard digits. We search the sea of decimals in the center of the grid for the closest match to our pattern. When we find it, we trace the row left and the column up to the top, revealing our raw digits, 7402. We use our gap matching trick one last time to find the final decimal, then use our scale tag to determine exactly where the decimal point belongs. The translation is complete. We started with an impossible calculation and extracted a precise answer using only our eyes and basic addition. Before computers, massive infrastructure like this steel bridge was designed using this exact system of manual translation. Engineers and architects spent their lives at drafting tables, manually looking up these digit patterns row by row to make their calculations possible. These tables acted as paper calculators, turning stacks of numbers into the bridges and machines that built the modern world.